Okay, so welcome back. Today we're doing Chapter 4, Field Theory, and we're going to start with vector spaces. I've written it all out here because it's a lot of writing, but these are generalizations of things you've seen in your class. I'm sure you've all had at least one class in linear algebra. We're going to fix a field, call it F, and a vector space, we'll call it V, is just a set that's an abelian group. Okay, that's what we call vector addition. And also, there's an operation called scalar multiplication. What that really means is you have a mapping from your field cross your vector space into your vector space. And then it gives you another vector called, so if you start with lambda in the field and V a vector, then we write lambda V for that element in V called scalar multiplication. It's in general just any function from F cross V into V, but we write it as just lambda V instead of some function of lambda and V. Of course, it has to satisfy properties that you'd expect. Number one, first of all, multiplication, scalar multiplication, is compatible with multiplication in the field. So if you first multiply the vector V by mu, under scalar multiplication, and then you scalar multiply by lambda, that should be the same as multiplying in the field, lambda mu, and then scalar multiplying. As a result, we tend not even to write those parentheses. Number two, the addition structure in your abelian group, the vector space V, the way you add vectors, is compatible with kind of a distributive law under scalar multiplication. So lambda times V plus W is lambda V plus lambda W. And number three, the addition in the field is compatible with scalar multiplication. So if you first add in the field lambda plus mu and then scalar multiply by V, that's the same as lambda V plus mu V. In other words, it just makes it look as if the distributive law is happening. And finally, number four, the identity element in your field multiplies any vector and leaves it alone. As usual, we call elements of the vector space V vectors and elements of the field F scalars. All right, let's do some examples. So you had a whole class on linear algebra, possibly multiple classes, but any of the things you studied there that you called vector spaces are vector spaces. They tended to be vector spaces over R or over C. So for instance, Rn is a vector space over R. Cn is a vector space over C. Anyway, up to isomorphism, as I'm sure you showed in the class, over R and C, those are the only finite dimensional ones. But anyway, all those examples are still examples of vector spaces. Another example is the set of polynomials f of x over a field. This is a vector space over a field f, over the field f. And here you're treating f of x as if it just has addition. That's the vector addition that it has. Okay, so our last example, well, really a whole family of examples, is the one that's really going to occupy our attention for this whole chapter. And that's when you have one field contained in another. So suppose F is a subfield of the field K. So the point is K is, at the minimum, an additive group. So that's the start of the vector space structure. And then multiplication by F will satisfy all the properties that we need to make K into a vector space over the field F. So, for example, R is a field contained within C, and therefore C is a vector space over R. In fact, as we'll find out later, it's just isomorphic to R2. And then one of the most common types of examples that we'll be dealing with, Q, is a subfield of Q attached root 2, and so Q attached root 2 is a vector space over Q. All right, now we've got some definitions that you used in linear algebra, and we're going to use the same ones. The first definitions are linear combination, span, things like that. So here we go. So first start with any non-empty set X of V, so some collection of vectors. So a linear combination of these vectors is anything that's a sum of Ci Vi for any scalar Ci in your field and any vector Vi in X. This is any finite sum of the vectors in X, even if X happens to be infinite. So we'll write SP sub F for the span of F, meaning the set of all the linear combinations. And we'll say that X spans V if the span is all of V. Okay, so when there's a finite spanning set for V, then it's called a finite dimensional vector space, and we say the dimension is just less than infinity as notation. Otherwise, we'll say it's infinite dimensional. For example, let's start with C. As we know, it's a vector space over R because R is a subfield. Then, of course, 1 and I span C because every complex number is obviously a linear combination over R of the vectors 1 and I, namely A plus IB is usually how we write it. So those two vectors span, and therefore C is a finite dimensional vector space over R. All right. Next, consider Q adjoin the root 2. It's a vector space over Q. Since we've seen everything in Q adjoin the root 2 can be written in the form of A plus B root 2, where A and B are rational. That's just saying that 1 and square root of 2 span this vector space. And since we have a finite spanning set, it's therefore a finite dimensional vector space. Well, let's turn to an infinite dimensional one. The set of polynomials with coefficients in F is a vector space over F, as we've said. But any finite collection of vectors will have a maximal degree, and therefore their linear combinations will only be able to get at polynomials of that degree or less, at best. And therefore you'll miss most polynomials. As a result, it can't have a finite spanning set, so it will be infinite dimensional. Okay, so now let's go on. As you remember, next comes linear independence, so let's turn to that definition. So for a non-empty set X, again, collection of vectors, we say they're linearly independent if and only if the following statement is true. It's only possible to add up a linear combination of elements in X and get 0 when you actually started with 0 coefficients. So, in other words, the sum of Ci Vi can be 0 if and only if all the Ci's are already 0. When that happens, then the set X is called linearly independent. Otherwise, of course, we'll say that the set X is linearly dependent. As is often the case in math, there's sometimes a disconnect between the way we write things down and the way we think about them, or the way we prove things versus the way we think about them. So I want to make a comment about that now. You'll do this in the homework, but here we go. First of all, let's look at the case when X is just a single element. One thing you'll prove in your homework, and it'd be straightforward, that if you have a single vector, then that vector is dependent if and only if it's 0. All right? The more interesting case is when you have multiple vectors. So what you'll prove in your homework, when you have at least 2 vectors in your set, which is usually the case, then those vectors are dependent if and only if at least one of them is a linear combination of the others. So you should really think of dependent sets as you have some vector in there that's not needed because you can get at it by linear combinations with the others. Okay, so last part of the definition. Once we have linear combinations and independence, if you'll remember from linear algebra, we're of course led to a basis. All right, so whenever you have a set B, if it both spans and is independent, we're going to call it a basis. And we'll say that the dimension of V is the cardinality of that basis. Of course, this definition has a huge problem. We don't yet know that if you have different bases that they have the same cardinality. So we will prove that essentially in a minute. But ignoring that problem for now, dimension is simply the number of elements that you need for a basis. I also want to mention that if you're working with finite dimensional vector spaces, the fact that bases always exist is easy. So that's a homework problem. But for finite dimensions, no problem. There always is a basis. However, for infinite dimensional vector spaces, that's not automatically the case. For infinite dimensional vector spaces, you need some further axioms that govern sort of how you handle large infinities. So if you have the axiom of choice, which essentially all mathematicians who are kind of working mathematicians just use for convenience, if you have the axiom of choice, then in fact you always have a basis as well. Okay, let's do a couple examples here. Let's start with C as a vector space over R. We already know that the collection of vectors 1, I spans C over R. And what we're going to do is show that, in fact, they're independent, and therefore it'll span and be independent, and therefore be a basis. And since there will be 2 elements in the set, then the dimension of C over R is going to be 2. Okay, so how do we do this? We start with the definition. This just means we have A times the first vector and B times the second vector, where A and B could possibly be anything in R. We want to show that this means A plus A and B are actually both equal to 0. However, if you think back, this is the part of the definition of C. The only way A plus IB is 0 is when A and B are 0, so we're set. These are in fact independent vectors, and therefore the dimension of C over R is 2. Since we know, of course, you have this geometrical picture in your head that the complex numbers are also the R2, that is the plane, by pairing A plus IB with the coordinate A comma B. So that's a 2-dimensional space, and so we expected this answer. Let's go to something a little bit more interesting. How about Q attach root 2 over Q? We already know 1 and root 2 span everything. And the question is if they're independent. And again, if they're independent, then that makes this set a basis, which makes the dimension of Q attach root 2 over Q 2. All right, so we look back at the definition of what do you do to check if something is independent. You have to show that the only way you can get a linear combination to be 0 is if each of the coefficients is 0. So start with a linear combination that adds up to 0. Okay, so suppose A plus B root 2 is equal to 0. We want to show that A and B are equal to 0. Well, if A plus B root 2 is 0, then, of course, you can write B root 2 is equal to minus A. And if B were equal to 0, then you, from the same equation, would immediately deduce that A was 0, and you'd be done. You'd get A and B equal to 0. On the other hand, if B were not equal to 0, then you could solve for root 2 as minus A over B, which would be a rational number. And as you know, that's not possible. So you see here the dimension of this field extension, Q root 2, Q adjoin root 2 over Q, has to do with sort of a very interesting fact about the numbers, that square root of 2 is not actually rational. In any case, 1 and root 2 are independent, and therefore that gives us a basis, and the dimension is 2. All right, let's go on to a theorem. Let's go ahead and start with V, a non-zero vector space, over a field F. First of all, bases exist. And any two bases have the same order, so that will make the definition of dimension well defined. Okay, part one. So we're starting with a finite dimensional vector space. In particular, as part of that hypothesis, that means there is a finite spanning set. Let's call it X. Now, if none of the vectors are a combination of the others, then it would be independent. Otherwise, one vector is a linear combination of the others. And if we therefore drop it, the span won't change. So, again, if you have a vector that's a linear combination of the others, drop it. You won't change the span. And then you repeat. And since we have a finite set, you can't do this forever, so you eventually have to arrive at a point where all the vectors are not combinations of the others, and they're still spanning, and therefore they're a basis. For part two, we're actually going to prove a lemma. Here's the lemma. So the lemma is that if you have a spanning set with n vectors, v1 through vn, and an independent set with possibly different vectors, w1 to wm, that are independent, then the number of things in the spanning set has to be at least as big as the number of things in the independent set. In other words, n is greater than or equal to m. If we have this lemma, then suppose we had two bases, b1 and b2. Then, of course, b1 at the very least spans, and b2 at the very least is independent. So the order of b1 is at least as big as b2. But the reverse is true. b2 spans, and b1 is independent, so that means b2 is at least as big as b1. And so the result is that they're equal. And therefore we just have to check this lemma. Okay, let's start with w1. w1 can't be 0, or else it wouldn't be independent. That's trivial. And since it's non-zero, and since the v's span, then we can write it as a linear combination, and at least one coefficient has to be non-zero. And that one coefficient, we might as well relabel things. I mean, some ci is non-zero. Relabel things so that its c1 is non-zero. All right. Since c1 is non-zero, we can move c1, v1 to the other side and w to the other side and divide by the c1 and get the following. But this just means, oh, I have to divide by c1. Okay, there we go. So this just means that that v1 is a linear combination of all the other v's and w1. That means I can, if I had v1 in the other v, if I had w1 and the other v's, then I could recover v1. And then v1 with all the other v's, of course, spans. So what this really means is that I can essentially throw out v1 and put in w1 and still have a spanning set. All right, let's turn to W2. That means W2 can be written as a linear combination of this new spanning set. I'm going to still use C's for this. They're different C's. So W2 is a combination of W1 and the remaining V's. If all of these CI's over here were 0, that would mean that W2 would be a multiple of W1. And that's not possible because they're independent. I mean, if you move it to the other side, you'll get a non-trivial linear combination. So that means at least one of these CI's over here has to be non-zero. We might as well relabel things so that C sub 2 is the non-zero one. All right, so we've got W2 is a multiple of W1, some non-zero multiple of V2, and a bunch of the other V's. And now we do the same trick. We can solve for V2. In other words, you can write V2 as the first W's and then all the other V's. And as a result, this set here, the W1, W2, and the rest of the V's, have to span, because if I just had W1, W2, and the rest of the V's with linear combinations, I could recover V2, and we already know that if I have W1 and V2 and the rest of the V's, then they span. So, W1, W2, and then the rest of the V's, that set spans V. And now you can see where this is going. You keep doing this, and eventually you get to the following. So this gives you a spanning set where you've put all the W's inside of this set. And of course, I mean, these guys may be empty. They may not be here. But the point is, if you're able to put all the W's in a one-to-one exchange into the spanning set, that means you had to have at least as many spanning vectors as independent vectors. And that's the end of the proof. So that lemma, as we've already said, proves the theorem.